of 3.5 and 3.6, so just measures of position in a data set. All right, so quartiles. So quartiles are measures that divide ranked data set into 4 equal parts. Okay, so think about a quarter. You have 4 quarters for $1. You have 4 equal parts in a data set. Okay, now you're not going to have Q1 through 4, so it's actually there's 4 different quartiles. Okay, but we're going to only indicate Q1, Q2, and Q3. So here's what we're going to do, and this is based off of the medians. So Q1, quartile 1, is the median of the first half of the data set, which is also the 25th percentile. Quartile 2 is the median. Okay, this is the 50th percentile. Quartile 3 is the second half of the data set, so that is going to be the 75th percentile. Okay, so let's just say, for example, we have a data set, and we'll make this pretty simple. We'll do, let's do like test grades. Okay, let's just pretend they're test grades. Okay, I'm only going to do 5 just to make it really simple. So let's just say you've got like a 64, 72, 80, 88, and 98. Okay, so I'm going to put this data set, okay, it's already in order. So the first thing I would do is I would find the median. So my median is right here in the middle. Which is also Q2. So then this data is separated into 2 different parts. You have the bottom half, okay, so everything below the median, and then you have the top half, which would be everything above the median. So if you scored above the median, then you did good. If you scored below the median, you did bad. Okay, so this is my bottom 50%. The median of this is quartile 1. So this is the bottom 50%. Okay, this is the top 50%. Let's go ahead and find the median of this. So the median of '64 and 72, we would do 64 plus 72, and then divide by 2. So 136 divided by 2, that would be 68. So that would be my quartile 1, the median between the bottom 50%. Let's say we do the same thing here, 88 plus 98 divided by 2. So that would give you 186 divided by 2, 93. That would be your quartile 3. Okay, so we have our data, quartile 1, 68, quartile 2, 80%, quartile 3, 93%. So if I'm taking that and then I'm projecting that data onto a set of 100 different grades, and you want to compare your grade, well, the 25th percentile is a 68. So if you scored a 67, okay, you scored in the bottom 25th percentile. So out of 100 students, 75 did better than you. 25 did either the same or worse. Okay, if you scored an 80, half and half. 93 is the 75th percentile. So in order to score in the highest 25th percentile, you would have had to get above a 93. Okay, so you're basically taking, we can do it very simply on a number line. You have your lowest score, I guess you could do the lowest possible score, 0. The highest possible score, 100. And then you would separate that into 4 equal parts. Okay, you've got this is your bottom 25th percentile. Here's another 25%, that's between 25 and 50. This is 50 to 75. And then this is 75 to 100. Okay, and then you'd mark this, quartile 1, and these are in percentiles, not grades. So quartile 1 would be at a 68%, or we won't use percent, we'll just use a grade. Quartile 2 would be at an 80, and quartile 3 would be at a 93. Okay, so you've got these 4 equal parts, and you can see where your data falls, what ranking it falls in the data. Okay, and that's just a very simple way to go about doing that. So we can do a lot more with the data, which we're going to go through here. You have the interquartile range. So that is going to be the range of the middle of the data set. My pen. I lost my pen. There it is. All right, so middle. Okay, so in this case, you would do interquartile range, which is abbreviated IQR, quartile 3 minus quartile 1. So in this case, you would just do 93 minus 68. And we get 25. Okay, so between the 25th percentile and the 75th percentile, there's a dispersion of 25 points, okay, from 68 to 93, which basically means if that's the middle of your data, that's where most of the kids scored, if you're looking at test grades. Most students got between a 68 and a 93 because that's the middle 50% of your data. Percentiles, so the measures that divide ranked data into 100 equal parts. Okay, the percentile desired tells us the percent of data values that lie beneath a certain observation. Okay, so if you score in the 100th percentile, you get the highest grade. Okay, if you score in the 50th percentile, again, right in the middle. Okay, if there were 100 students, if you're in the 50th percentile, 49 did better than you, 49 or 50. 50 did better, 50 did less. You're right there in the middle. Percentile ranking. Okay, so this would be to find where you are within a data set. So you have P of K, so that's how you would say that. P of K is a number, or P sub K, that represents a location of the desired percentile of the data set. So find the location first. Okay, and the location is going to be N times K. So N is the sample size. So let's say you had 100 students, that would be your N, and then K would be the percentile desired. Okay, and then if the location is a decimal, just round. And then using this location, find the actual value of P of K. So for example, to find the location of the 35th percentile in a data set containing 200 observations, what you're going to do is you're going to go, okay, N is your sample size, that would be 200 observations, times 35, and then divided by 100. Okay, so 200 times 35, I think, is 7,000. and then divide by 100, and you get 70. So it would be the 70th value in the data set. So for example, let's say you wanted to find the location in this data set, okay, of the 90th percentile, the 90th percentile, and we'll say there's 100 observations. Okay, so 90th percentile. So what would you need to get on the test in order to score in the 90th percentile? Okay, 100 observations, so that would be your 100, or your n, 100. You would go p sub 90 equals 100, that's your n, times 90 divided by 100. Now with 100 observations, that one's 90. So it would be the 90th one. If you ranked them all, you put them all in order, it would be the 90th one. Okay, if that changes, so let's say it's an n of 100, or sorry, 150. You would do 150 times 90 and then divide by 100. So 135. So it would be the 135th in your data set. So you'd line it all up and then you'd count, or I'd probably count backwards from 150 because you'd be faster, and get to the number that's in the 135th position and go from there. Now the percentile rank is going to be the total number of values less than this value times 100 over n. So what that looks like would be like this. Let's say the percentile rank is 18. Sorry, we'll have to look at the data set for this. So we want the percentile rank of the value 18 in this data set. Or if you go back, oh, I don't have all 100 grades here, so we're going to move on to one with actual data. All right, so in this data set, we want to find the rank of the number 18. So here's what we're going to do. We're going to first rank the data, so let's put it in order. So our smallest observation is going to be what? 10. Okay, so 10. And I've got 2 of those. Yeah. All right, then we got 11. 4 of those. Then we have 14. 15. Then it looks like 18's next. So you've got 1, 2, 3 18s. You have 2 19s. And then you have a 20. 2 20s, sorry. Okay, so we want to find, let's say, the percentile rank of the number 18. So what you're going to do, you're going to find the number 18. It's right here. There's 3 of them. Okay, it doesn't matter how many there are. How many are below that? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 values below that. 18. Just count these. So total number of values less than this value would be 8 times 100, and then over the sample size. How many total did we have here? 15. So we had 15 values. Okay, so we had 8 values less than the number 18 times 100 over 15. So that would be 800 over 15. So 53.3%. So the percentile rank, and we'll just do whole percentiles, would be in the 53rd percentile. Okay, now hopefully these aren't grades, or let's just say it's out of a 20 question test. It's just the raw, not the percentage. Okay, so we get 18 out of 20 right, 53rd percentile. Yes, that's your sample size. Okay, let's say we want to go back up to here to find the, actually we can do it down here. We'll do it with these. Okay, so let's do the data with all of these. The median, that's going to be our middle number, so there's 15. Yes. Well, that's a very good question. It's basically the equation worked backwards. Where did my mouse go? So they're different equations. See, this is finding the percentile rank from a number. This is telling me the location of a percentile. Okay, so let's say I did that. So I wanted the location of the 53rd percentile. This is the formula that I would use for that. So here I would go for 53rd percentile, P sub 53. I would go, N would be 15 times 53 over 100. So 15 times 53 over 100. So it's telling me 7.95. If we have a decimal, we're going to round up. So this is the 8th location in the data set. So when we do the percentile ranking, there we go. When we do the percentile ranking, it's not telling us what the number is, it's telling us the location of the number. So this is the 8th number or 8th value in the data set. So if I go to my data ranked, I go 1, 2, 3, 4, 5, 6, 7, 8. The value in the 8th position is the number 18. Okay, so it's almost like it's backwards. They're reworked equations. So one is to find the location of the percentile. The other is to find the percentile based off of the value. In order to do that, you have to find the location first. That's the 7th number. 1, 2, 3, 4, 5, 6, 7, 8. Oh, you're right. Well, it might be because of the 53.3. Which would still give us the 8th number. Percentile, location. Let's try this again. We'll do this with this one. And let's see. It might be that we have to go to the next one after that. But let's take a look. Okay. Well, we'll come back to this. Let's look at this. We'll come back to the median and stuff first. Let's look at this right now. So the 20th percentile. Okay, so that would be P20. So that's what we're doing right here. Let's do these ones in blue. All right. So P20, we would do the 20 would be, or sorry, our sample size would be 15. 20 would be the percentile. And then we are dividing by 100. So 15 times 20 would give us 300. Divided by 100 would give us 3. So that would be the 3rd value, which would be 11. Now I want to work that backwards just to make sure. So let's work that backwards then. So we want the rank of the number 18. There are two values less, or sorry, the number 11. There's two values less than the number 11. So we would do 2 times 100, which would be 200, divided by 15. And that would be the 13th, so it is not going to work backwards. Okay, so they're not exact backwards equations of each other. Okay, but they're going to, that is the 13th percentile. I mean, because there's so little data, you could say this is probably in that range of 13th to 20th percentile. It just doesn't work exactly if you work them backwards like that. I'm not going to give you, sorry about that. I'm not going to give you a question where you're going to have to do both of them one after another. So it'll be separate data sets. But that's a good observation. I always just going straight through it. Probably because I've never given a question like that. I haven't had that question. Did you have your hand up? Okay. All right, so let's take a look at, so this was the number 11. And the 85th percentile, okay, we do P85. And let's see, so you have 15 values. You want the 85th percentile over 100. So 15 times 85 would be 12.75. So they're in round up. So it's the 13th value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's this one here, 19. And then now that I think about it, I think that as the sample size grows larger, if I'm just looking at the equations and thinking about the algebra, if I had like 400, then those would be a lot closer. There's only 15 data values here, so it would be a lot closer. So if I look at this just real quickly and I rework these, so you've got 400 times 20 over 100. It would give you the 80th value in the set, so 80 out of 400. And then let's see, the rank of the number, let's just say the number was 80th, there were 79 values less than that. 79 times 100 divided by 400. And then it would be the 19.75 percentile, which we would round up to 20. So then they're a lot closer to each other. So the greater your sample size is, the closer those values are going to be to each other. Does that make sense? And we're going to look at that a lot more in chapter 8 and chapter 9. So really, and then one thing you do want to look at just when you're reading a statistical article is the sample size. Okay, a sample size of 15, not that great. You want a minimum sample size of 30 to really do any sort of predictions, which is actually pretty small. So real good samples are going to have at least 100 to 1,000 in the sample data. And then the more and more you have, the more accurate you could say your data is. Okay, so let's look at the percentile rank of the value 18. So 18 is, oh, we did that already. Let's look at 14. So 18 we did up here, that was 53%. 14, let's see. So 14 we do there are 1, 2, 3, 4, 5, 6 values less than 14. So 6 values less times 100 over 15. 40. So it would be the 40th percentile. All right, and let's do the quartiles here. I'm going to show you how to do this in your calculator. All right, so let's go ahead and pull out our calculators. And this can also be done in lists. Okay, so you're going to go to Stat, then Enter, so Edit. Okay, if there's nothing, or if there is something up here, again, just highlight it and hit Clear. Do not delete the list. Clear. All right, and then we're going to put the data in. You can do it raw, or you can have it in order. 4 11s, 14, 15, 3 18s, 2 19s, 20. Yeah, 15. Okay, once you get that entered in, go back to your home screen. So second bit. And it's the same way that you would find the standard deviation and variance. So Stat, scroll over to Calc, enter one variable statistics. You want the one variable statistics from L1. If you're using a TI-84, you just put nothing in the frequency list. Okay, and then look, scroll down. There it is. Okay, so your quartile 1 is 11. Your median is 15, which is quartile 2. Quartile 2 and the median are the same thing. Your quartile 3 is 19. Okay, so it's going to give you that data. And then your minimum is 10, your maximum is 20. Okay, so let's write that down. So you've got your median is 15. Quartile 3 was 19. Quartile 1 was 11. The interquartile range is Q3 minus Q1, so 19 minus 11. So that's going to give you 8. Yes, so do you have your list entered? Okay, so once you have your list entered, you're just going to go same thing you did for standard deviation and variance. So Stat, then over to Calc, then one variable statistics, and you want the one variable statistics for L1 or whatever your list was named. And then just scroll down. It's underneath all of the standard deviation stuff. All right, and then you can take this, you can actually graph this data, and that's kind of what I was doing up here. We're going to make it a little bit nicer. So you have a box and whisker plot. So the visual representation of your data shows the center, the spread, and the skewness of a data set. It's also going to show any outliers. Remember we talked about outliers? We're going to have an actual test for outliers, which we'll do at the bottom. So we're going to do this with this data right here. So let's just say this is, we'll do the ages of all of the grandchildren in a family. That looks like it's something that we can relate to, right? All right, it's a lot of grandchildren, but that's okay. All right, so we're going to rank it first. So the youngest is 3. Then you've got, let's see, you've got a 5. You've got 1, 2 6s. You've got a 7. You have 1, 2 9s. You have a 10, an 11, 12, 14, and 15. All right, smallest value is 3, largest 15. Are there any obvious outliers? Doesn't look like it. Okay, let's find the quartiles. So we can do this one by hand. Let's see how many grandchildren we got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so 12. And then just for a note on the test, I think the largest data set I give you is like 20 values. So all of it you can do by hand if you have to. All right, 12. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Median of 9 and 9 is 9. So that's my median, so that's Q2. All right, so let's split this data. So this is going to split there. So you've got 1, 2, 3, 4, 5, 6 on here. So your two middle values on this side are 6 and 6. So Q1 would be 6. And then on this side, you've got 9, 10, 11, 12. So right here in between 11 and 12. So what's the median of 11 and 12? Yeah, 11.5. So here's how you make a box and whisker plot. You have a line down here. On the very end of the line, okay, you're going to draw like a vertical mark. You're going to put your lowest value, so 3. And then over here, you're going to do your highest value, 15. So that's a spread of 12. So I want to make 12 marks. So we've got 4, 5, 6, 7, 8, 9. I probably did a little too short. 13, make a big jump there. 14. Yeah, that's fine. All right, so you're going to mark the data. Okay, the next thing you're going to do is mark your quartile 2. So that's going to be 9. So just kind of above here, just make like a little mark. Okay, then your quartile 1, same thing. And your quartile 3, same thing. And you're going to take that, you're going to connect those marks, make a little box. There we go. All right, so there's your box. And then you're going to draw a line from the box to the smallest value, and then another line to your largest value. And that's a box and whisker plot. You can create this in your calculator. I do have a video on YouTube about it. I'm not going to spend time on it in here because this is the only time you're going to do it, just maybe one question. So if you want to learn, I did add a section on Blackboard with calculator tutorials. Let me show you that real quick. I meant to show you in the beginning of class. So in your class, in class recordings, there's a folder that says calculator tutorials. And these are like specific calculator tutorials. So box plots, and it'll link to it. So the first 3 are stuff that we have covered. This stuff we have not covered yet, so don't watch it yet. And I'll add some more as we go through. Okay, but for standard deviation and variance, grouped and ungrouped, and then box plot, that's pretty much all we did, because these first 2 also go over doing lists as well. Okay, so there's your box plot. Now let's talk about the outlier test. All right, so to determine if something is actually an outlier, you have to do something a little more than just look at it and say that is really big or that is really small. Okay, so there is a test for it, and here is what the test is. All right, so there's two different outliers. You could have a small one or a large one. It would be quartile 1 minus 1.5 times the interquartile range, IQR. And then the other outlier would be large. It would be quartile 3 plus 1.5 times the interquartile range. Okay, so it's plus or minus 1.5 times the interquartile range. Okay, so the IQR for this data set we can do on this one is, let's see. Remember, that's Q3 minus Q1. So that would be 11.5 minus 6, so 5.5. So if we wanted to test for true outliers in this data, you would have quartile 1 is 6 minus 1.5 times 5.5. So we could just put that in our calculator. 6 minus 1.5 times 5.5. So negative 2.25. So if there were any values on this data set that were less than negative 2.25, it would be a true outlier. Obviously, in our context, if we're talking about ages, that's not going to happen. Quartile 3, you have 11.5 plus 1.5 times 5.5. So we can put this in your calculator as well. 19.75. So if you had a 20-year-old, that would be an outlier in your data set. Okay, so it would have to be smaller than this number. So if it's less than, we could say, less than negative 2.25 or greater than 19.75, then it would be an outlier. And that's how you test for the true outliers in your data set. All right, so I believe we have some questions to work on. So I'm going to give you guys some time to work on those. And then we'll go over that. Okay, let's take a look at these problems. So we have a box plot. It's a 2 box plots, okay, separated by males and females, and it is in a class, okay, and it is the weight of these students. Okay, so we want to go, which of the following is correct? So let's take a look at these. About 50% of the male students have weights between 150 and 185 pounds. Would you say that is correct? Where's 150? Right here. And 185 would be 180. 180 is right here, so would this be 185? What does the interquartile range represent? Right, which is the 75th percentile minus the 25th percentile, which is the middle 50%. So that is correct. That's 150 to 185. Okay, that's the middle 50%. This box is the middle 50% of your data. Yes. It's not 50% of the graph. Okay, but if I were to take this and separate it out based off of the data, this is the 0 or 1 percentile. Okay, this is the 25th. This is the 50th percentile. This is the 75th percentile. And then this is the 99th percentile. Okay, so what we're seeing here is that you've got a couple of really skinny kids and you've got a couple of fat kids, but most of them are right here in this range. It's your middle 50%. Okay, because Q1, remember Q1 is your 25th percentile. Q3 is your 75th percentile. So if you subtract that, that gives you 50%. Now, I do want to go back because I was looking at the test, and there is something on here that does generally confuse students. So go back right up here with percentiles. So percentiles, when we're looking at a graph, there's 100 equal parts. But how many percentiles are there? There are 99 percentiles. 99 percentiles divided into 100 equal parts. I know it can be confusing, but that's because you have the first percentile and then the 100th percentile, which gives you 99%. So you have 100 equal parts with 99 percentiles. I don't know if I can project it, but the growth charts, they'll show you if you're in the 99th percentile, that means basically you're the 100th percentile. That's the highest you can go as far as percentiles, but it's in 100 equal parts, because if you're in the 99th, that's the top one. I don't know if you can see it like that, the growth. So it's 99th would be the top one. That's my child's head. Yes. I'm sorry? Yes, that's what I was just showing you, is that the growth chart. It's based off of, you know, a database of data, the average size kind of thing. Yeah. My child's head is above the thing, but it says 99th percentile, but he has a really big head. Yeah. Okay, so that one is correct. So the next one, 25% of the female students weigh more than 135 pounds, or 30 pounds, sorry. So let's look for 130. Okay, that's right here. Oops. All right, so here's 130. It's right here on there. I'm going to say it's right here. Okay, if this is remember this is Q1, Q2, Q3. So Q3 is the 75th percentile. So greater than 75 here would be 100, because that's the end of your data right here. All right, so that would be 25%. So that is true. Yes. Percents. It's not really. It's not, the graph isn't going to show you, it's showing you the skewness when you look at the graph. Like if you look at this, see how quartile 3 from Q2 to Q3 is larger than from Q1 to Q2. So you can say, well, there's going to be more kids in here because that's larger. So it's showing you skewness in the graph. It's not going to be an exactly even graph, because then you really wouldn't have any variation in the data. If you look around at everyone, you know, everyone is different sizes, so the variation isn't shown in the graph. This is not a normal distribution graph, okay? So this is showing the skewness. So this is showing the percent of the data, and then this is the bottom, or the minimum, and then the maximum. So it's not going to be right in the middle. The 50 at the median isn't going to be like if this was, well, you could look here, right between 80 and 240, okay, the median's not going to be 160. Okay, the median is over here at 120. So it's not exactly 50% of the graph. Okay, it's showing you skewness. Does that make sense? No. Okay, well, give me a minute. Well, I think we might have one on the review. But if we create a graph, it might be a little bit better. Okay, it's just we'll have to get a larger set of data. We could do one in the calculator, actually. We'll do that in a minute. All right, the median weight of male students is 162 pounds. So where's the median? It's right here. Does that line up with 162? It's close enough. It's like right there. So we're going to say yes. The mean weight of female students is about 120 pounds, because of symmetry. So this is where, okay, if you look at these two boxes, you're going to see this here. So this is pretty even. It's a little bit more skewed here, but this is not even. Okay, you've got a lot more in this area than you do over here. So because of symmetry, we're going to say, yeah, the mean and the median are going to be really close to each other because these are very close sized boxes. So we're going to say yes. All right, and then that means E, all of the following are correct. Okay, so let's do the box plot with some data so we can look at this. So let's just say we've got, I'm going to come over here, and we'll do the same thing. So we'll do weights. I'm going to do 10 values and see what this looks like. So I don't know, we'll start with 100. We'll do a 105, 110. Let's do a couple 120s. 1, 2, 3, 4, 5. Let's do a 135, 140, 145. 2 more. Let's do a 170 and let's do a 160 and a 170. All right, so you've got 10 values here. So when I rank these, let's find the median. Okay, so these are my 2 middle values. So my median is going to be 120 plus 135 divided by 2. So that's 127.5. Okay, then let's find quartile 1. Okay, so let's split this right here in the middle. So quartile 1 is going to be 110. And quartile 2, or sorry, quartile 3, 145. All right, now if I am putting this on a symmetrical graph, okay, here is, we'll do 100. We're going to go in tens. I'm sorry, lost track. 30. Okay, so our median is not in the middle of this graph. Okay, this graph is pretty symmetrical. I can't erase the end of that, but I tried to space these out evenly. Okay, the middle, if I look here between 100 and 170, that'd be 135. Okay, if I did 100 plus 170. Okay, so that's not right in the middle, but I'm doing the median. So the median is not the same as the mean. So that's 127. So that's going to be about maybe right here. Okay, so you're already looking, this is not a symmetrical graph. Okay, then you have quartile 1 is 110. That's going to be right here. And then quartile 3 is 145. So about right here. And then there's our graph. Okay, so this is, you can look here, this is your 25th percentile, okay? This is your 50th percentile. This is your 75th percentile. Okay, and then this is going to represent 50% of the data, but it's not, okay, if you added all of these together, you would have, well, your mean would be right here. Okay, so it's not symmetrical. Now these boxes look fairly symmetrical, but sometimes if your median is slightly skewed, oopsies, didn't mean to do that, then the line might be somewhere over here. Okay, but if you look at the graph, sometimes you've got a tail here. This might have an outlier. So sometimes if you see a graph that has a longer tail on one side, you're going to have an outlier. But it just depends on what your data looks like. So let's say we didn't have this, all we had was the graph, then all we have to go off of is this. So you could say, okay, the 25th percentile is 110, the 75th percentile is 145, okay, our median is about we'd probably say 128 if I'm looking at that. And you know, your smallest value is 100, your highest value is 170. You don't know what the data in between looks like, okay, because now it's not given to us. So you have to make inferences based off of that data. So here I could say, well, 50% of my data is between, okay, in here, 110 to 145. Okay, my median is right here, about 120, what did I say, 128? Okay, so if you look at it backwards, it is a little harder because you do have to make inferences about your data because you don't know what the actual numbers look like. Okay, so, but if you do have the actual numbers, then you can make the box, you can see how the box is made. So just going back and forth with it helps to understand it a little bit better. But like I said, with the box plot, you might have a question like this, maybe one or two questions, but that's about it. You don't really have to know how to construct them, just kind of what the percentiles would be based off of that. Does that clear up a little bit? Cool. All right, let's take a look at number 2. So outliers. All right, so for this one, we want to find Q1, Q3, and the IQR. So I think the fastest way to do this is I'm going to put this in the calculator because this is a bit larger. So stat, enter. Okay, I'm going to go up, highlight L1 and clear, enter, and then I'm going to put this in. 14, 17, 37, 45, 51, 52, 53, 56, 56, 57, 60, 63, 65, 67, 89. Okay, so it looks like there's 15 values. And you just want to make sure, because it's really easy to miss one. All right, 15, good. Okay, so then I'm going to go back to my home screen. And then you run the one variable statistics. So stat, over to calc, enter, and then second L1. And then scroll down. So we've got Q1 is 45, Q3 is 63. So that's really all we need for outliers, Q1 and Q3. So 45 and 63. Okay, so based off of that, my IQR is going to be 63 minus 45. So 18. And then we want to test for outliers. So you're going to do for your small outlier, you're going to go Q1 minus 1.5 times your IQR. And then your large one, Q3 plus 1.5 times your, I don't know why I wrote, oh, I was writing 18, but IQR. All right, so quartile 1 is 45. So 45 minus 1.5 times 18. So 18. Are there any values less than 18? Yeah, 14 and 17. So those are outliers. Let's see if there's any here. Q3 is 63. So 63 plus 1.5 times 18. Oops. Plus 1.5 times 18, 90. Are there any values greater than 90? No. So 89 might look like an outlier, but you have to do the test just to be sure. So it's 14 and 17. All right, number 3. Suppose that taxis in New York are driven an average of 60,000 miles per year with a standard deviation of 11,000 miles. Assume the mileage driven is normally distributed. So now they're saying when they say assume it's normally distributed, it is symmetrical. Okay, the mean and the median are equal. Okay, so that we can put it on a normal distribution graph. And then how many miles would the middle 95% have driven in 1 year? And then I wrote a hint here, draw it out. All right, so I don't know why this didn't copy here, but here's your normal distribution curve. So this is using the empirical rule. Remember that 68, 95, 99.7, 1 standard deviation, 2 standard deviations, 3 standard deviations. All right, so the middle 95%, this is what we're looking for. 2 standard deviations. So you have the average is 60,000, so that's going to be right here. And then a standard deviation of 11,000. So let's draw that out. So 1 standard deviation, 60,000 minus 11 is going to be 49,000. 60,000 plus 11,000 is 71,000. Then we're going to do one more standard deviation. 49 minus 11 is going to give us 38,000. 71 plus 11 would be 82,000. Do one more just to finish it. 82 plus 11 would be 93. 38 minus 11 would be 27. Okay, so the empirical rule tells us that 95% of your data will fall within 2 standard deviations of your mean. So 2 standard deviations would be from here to here. So this is 95%. Does that look like 95% of this curve? Looks like it. All right, so we're going to say how many miles will the middle 95% of taxis have driven in 1 year? Between 38,000 and 82,000. That's a lot of miles. All right, and then we have one more question with IQs. Okay, IQ scores for adults aged 20 to 34 are normally distributed with a mean of 100 and a standard deviation of 15. So this is actual how they interpret your IQ scores. So the highest IQ score, I believe, is 160. I think the lowest is 40, maybe. Approximately what percent of people in this group have scores below 100? You don't need to draw this one out. If 100 is the mean, how many people are above? How many people are below? Come on, guys. Where's the mean here? 50-50. Good. So mean is 50-50. So how many people have a score below 100? 50%. 50%. All right, then we're using the same data for number 5. All right, IQ scores for adults aged 20 to 34. I wonder if that means your IQ goes down as you age, because I'm going to age out of that this year. All right, they're normally distributed with a mean of 100, standard deviation of 15. The minimum IQ to qualify for Mensa, which is that genius group, is 145. According to the empirical rule, what percentage of the population qualifies for membership? So, let's see, you've got 100. And we're just going to go, because we're going this way. So 1 standard deviation would be 115. 2 would be 130. And that 130 would be gifted. And then 145 is genius. And then you've got these values over here. Probably draw these a little too close together. Oops. Okay. So according to the empirical rule, what percentage encompasses 3 standard deviations? 99.7%, right? All right, so if this area in here, from here to here, is 99.7, how much is left over? Good, 0.3, because this is 100% under the curve. So 100 minus 99.7 would be 0.3. Now, of that 0.3, half of it is here on the left, half of it is here on the right. So 0.3 divided by 2 would be 0.15%. So it's less than 1%. Same thing over here. 0.3 divided by 2, 0.15% of the population. So 0.15% of the population qualifies for Mensa. Now think about that. How many people are in that age group? Probably what, 150 million? .15% would be 0.0015. So roughly 225,000 people. That's a lot. So it's not impossible. It's a very small percentage, but not impossible at all. All right, we've got about 10 minutes left. Let's do a few questions here.